This video is going to look at the problems from discussion 5 on the early reactions in alkenes and alkynes. A little bit of review with some alkene and alkyne nomenclature, making sure we're looking for the longest parent chain. And so in this first one, our longest parent chain is going to be 7 carbons. We have our alkene on position 3. We have methyl groups on position 2 and 5. Last part, remember that I have 1 hydrogen on carbon 4 that's pointing up. I have 1 hydrogen on carbon 3 that's pointing down. And so I have an alkene here that's in the E configuration. So when I put that all together, I have a double bond E-2,5-dimethyl-3-heptene. Next one's my alkyne. So here again, I'm looking for my longest chain. This is going to be 5 carbons. My alkyne is on position 1. I have 2 methyl groups on position 4. So when I put that together, 4,4-dimethyl-1-pentene. This next one is looking at DU. So I would use my unsaturation number formula. When we do that, we have 5 carbons. We have 8 hydrogens, and we have 2 oxygens. That's going to give us an unsaturation number of 2. When I think about my functional groups here, so I know carboxylic acid has 1 pi bond, so that means I'm going to have 1 unsaturation unit in my carboxylic acid. I have 1 also in my aldehyde, and so what I need to do for both of these structures is make sure that they contain 1 more degree of unsaturation. So you have lots of different possibilities for answers. I'm going to go ahead and draw my carboxylic acid. I'm going to need to have at least 1 more DU, so I used a double bond in order to make that happen. So I have an alkene here. And make sure your answer has a total of 5 carbons, 8 hydrogens, and 2 oxygens, and it should be good. For my aldehyde here, again, I kept my alkene. I also need to make sure I add another oxygen, so I have an OH as a possibility. I saw some answers that were dialdehydes that had 2 aldehydes. That should be good as well. Again, make sure you count your carbons and hydrogens to see if your answer works. More practice with curved arrows and resonance. So the first thing I would do would be to try to figure out why this nitrogen is positively charged. I know it's connected to 4 different groups. It's connected via the double bond, and it has 2 hydrogens. And so this nitrogen is positive because it's missing its lone pair. So I'm going to use these pi electrons and push them back onto the nitrogen in order to get that nitrogen its lone pair back and then a neutral formal charge. By doing that, that's going to put a positive charge on the carbon that it's connected to. My next resonance structure is going to now allow me to push over my pi electrons from my other alkene. That's going to shift the position of where the double bond is, and it's also going to create a positive charged carbocation on the other carbon that was a part of my pi bond and now no longer is part of my pi bond. Now I have a positive charge next to a nitrogen. This nitrogen is only connected to 3 groups, so that means it has a lone pair. So we're going to use that lone pair to push down to make a double bond. For our major contributors, remember that we want to focus on structures where all the atoms have octets, and so my carbocations in structures 2 and 3 are going to eliminate those possibilities. Notice here in this structure, every atom has an octet. This one, same thing, so we would say both of these are our major contributors. This next question is looking at asking us to draw the expected products for these reactions. Remember, these are going to be all of our Markovnikov addition reactions. So in our first one here, we're looking for which carbon is more substituted or which carbon is going to have more H's. So in this case, we have a carbon in our alkene that has 1 H. We have a carbon here that has no H's. So my hydrogen is going to go to the carbon with more H's, and my chlorine is going to go to the carbon with less H's. So that would be the answer for the first one. For the next one, we have excess, so we're going to need to add multiple HBRs to the same molecule. But in this one, the 2 carbons we're comparing are both the same type of substitution. So this carbon has no hydrogens, and this carbon has no hydrogens. That means we're going to form 2 different carbocation intermediates. The first one's going to have the positive charge here. That's going to add the bromine. The second one's going to have the positive charge here where the bromine adds. After that, we're going to add a second equivalent of HBr where the same rules apply. So we're going to add 2 hydrogens to the same position. In this case, I've added 2 bromines to the first position of my alkyne, 2 hydrogens to the second position. Since we make the same stability carbocation, we could also have the 2 hydrogens add to this position and the 2 bromines add to this position. We didn't have to worry about multiple products in the top one because it was clear which carbon had more hydrogens. Same thing for the bottom one. This carbon has no hydrogens. This carbon has 1 hydrogen. That's where the H is going to end up. So my chlorine is going to end up to the next position. If you had trouble seeing how the products were generated in the last question, this is giving you the full curved arrow mechanism to show how exactly we're generating our final product. So to get things started here, we know that our hydrogen is going to add to the position that has more H's. The bromine is going to add to the other position. In order to get this started, let's go ahead and draw out the bond between our hydrogen and bromine. Now we can have our pi electrons from our double bond go out and grab the H. We're then going to push the electrons from the HBr bond onto the bromine. Here is where our hydrogen is going to end up going to this position because it has more H's compared to this carbon. That means that we're going to end up with our positive charge on this position, and we've also generated a bromine from my second arrow here. At this point, I have my carbocation intermediate. We know that this serves as a really strong electrophile. I can use my Br- to make a new bond to the carbon that's positively charged, and that gives me my final answer in the box. So the mechanisms would be the same for the first and third questions in question 5. This question is actually having you work in reverse. So notice here I'm looking for only alkenes, and so what we're really asked to do is recognize that these are both alkene reactions, and we know that H2 with palladium on carbon is going to turn an alkene into an alkane. So what you were asked to do here was to provide all the different types of alkenes we could start with in order to make this structure. So really, we can go ahead and put the double bond between any 2 carbons. Here's my first one. So I have a double bond between these 2 carbons. Now notice we can't draw a double bond between these 2 carbons because that would be the exact same alkene. My next possibility would have the double bond between these 2 carbons, which would look something like this. Now my last possibility, I could also draw the double bond between these 2 carbons. Now in addition here, notice all 3 of these alkenes do not have E and Z stereoisomers. I have 2 H's on this position, 2 methyl groups on this position, and 2 H's on this position. If I did have the possibility for E and Z isomers, those would also be correct answers. That's what happens in this second one. So now I have to remember that this HBr is an alkene reaction, but I know that wherever I put the alkene, I'm going to want to make sure that this carbon is the more substituted carbon because that's where the bromine ends up. So I think the easiest one to see would be to have the double bond out to this position. So now I have a carbon with 2 H's, I have a carbon with no H's, I add the H here and the bromine here. I also could go ahead and put my double bond out to these positions. When I do that, I now have a carbon that is going to be connected to 3 other carbons versus a carbon with 2 other carbons. Another way to think about that would be this position has 1 H, this position has no H's. Now notice this is our first one. The way I've drawn this, I have my higher priority group pointing down, my higher priority group pointing up. So the way I've drawn this, this is in my E configuration. So I also could draw that double bond as a Z. So here, notice my higher priority group is pointing up, also pointing up. And this one has one other possibility, which we're going to talk about in question 9. But what we can also do here is we have the possibility to form a secondary carbocation at this position, and we have a tertiary position next door. And so we're going to end up doing a rearrangement. So if you're having trouble seeing how this last one was formed, I'm going to go through a very similar mechanism in question 9. 2 more predict products questions. So in the last ones, we focused on HBr and HCl. H3O plus is going to act in the same fashion. We're still going to add a hydrogen to the carbon in our alkene that has more hydrogens. So in this case, we have a carbon with 1 H versus no H's. So we're going to add an H here. Our nucleophile in this case is going to be water. After we add the nucleophile, we're going to deprotonate it. So we'll end up with our neutral alcohol. Our next reaction is using the Lindlar catalyst. In this case, we're going to take our alkyne and turn it into the alkene. Specifically, Lindlar is going to end up making your cis alkene. So make sure that you can draw your H's in if you want, but make sure that your 2 higher priority groups are both pointing in the same direction in order to draw your cis alkene. So here is an example of a rearrangement. We're going to do a hydride shift in this case. This will also show you exactly how that blue product from question 7 could also be a starting material alkene. In order to get started, we're still going to draw our same arrows as we did in our early mechanism. So let's use our alkene and go out and grab the hydrogen off of our HI. We're going to add the hydrogen to our terminal position here. This carbon has 2 H's, this carbon has 1. So that's going to end up putting the carbocation on this carbon, which is a secondary carbocation. At this point, I know I can't add the iodine here because my iodine needs to add to the carbon in the middle. The other thing I notice is that this carbon no longer has a hydrogen on it. It started with a hydrogen here, but it's not on this position in the product. So that's the hydrogen that we're going to have to move to the position that is our carbocation here. In order to show that with arrows, we're going to circle our hydrogen, and we're going to start our arrow at the bond between the carbon and the hydrogen. This is showing that the 2 electrons that are responsible for the carbon-hydrogen bond are going to be used to make a bond between the carbon that's positively charged and the hydrogen that's circled. Now that's going to end up putting a hydrogen on this position. So this carbon now has 4 bonds. This carbon only has 3 bonds. So that's why we have a tertiary carbocation on this position. We've formed a much more stable carbocation going from a secondary to a tertiary, and that's the incentive for doing this hydride shift. Now we have the carbocation at the correct position. We can go ahead and draw our iodine adding, and that's going to end up giving us our final product.